So this is the question from chapter 16. It's asking, use the following data to calculate the KSP value for each solid. The solubility of CaC2O4 is 4.8 E negative 5 moles per liter. Okay, so first let's start off with disassociating CaC2O4. Let me do that real quick. Okay. Okay. CaC2O4. Okay. And it's a solid. So it's gonna disassociate into calcium and its ionic charge 2 plus, and it's aqueous, obviously, and then as well as C2O4, which is ionic charge 2 minus. And as you can see, C2 plus 2 minus, it's cancels out. That's why in the CaC2O4, the reactant, there's no ionic charge. This is also aqueous. Okay. So now we make the I short. RICE. Okay. Let's make a line right here. So this just cancels out because it's S max. Because this is like the starting reactant that's disassociated. This is what gets disassociated. And we don't know the initial, so just leave that blank. The C plus S, and the reaction is shifting towards the right because of the Q. It's shifting towards the right. Like Q is right here. The KSP, whatever, it's right there. So it's going here. And whatever's on this side, it's negative. This becomes positive. So that's why the product side is plus S. If it was going towards the left, it would be, what do you call it? It would be, it would be negative. Like, yeah. Okay, so bring that down. S. Okay. So now that we have that, let me write the KSP. KSP is equal to the concentration of Ca2 plus and the concentration of C2O4 2 minus. C2O4 2 minus. Okay, that's the KSP. So if you hadn't noticed, I didn't write anything in the denominator. There is no denominator. If there's no denominator, that means there's no reactant. And the reason why I didn't write the reactant because it's a solid. You write the aqueous solutions, or if it's a gas. If it's a gas, you write the partial pressure or the pressure, but you don't write solids. So this is the products. If you look at the E for Ca2 plus right here, it's just S. For C2O4 2 minus right here, it's just S. So the concentration for these two, we just know it's S. We don't know what it is yet. So KSP. minus P is equals to S, which is S squared. Excuse my terrible handwriting. Okay. If you look up here, 4.8, it says 4.8 E negative 5 moles per liter. This is talking about the S. This is talking about what we're plugging into S. This is the mole. Okay, so we need to find KSP, right? And we know KSP is S squared. So we know S is equals to 4.8 E negative 5 moles per liter. 4.8 E negative 5 moles per liter. Okay. So let's just plug that in. KSP is equals to 4.8 E negative 5 squared. Don't forget the squared. And let me do that in my calculator real quick. So you actually end up getting 2 is equals to 2.304 E. That's an E, negative 9. That is the KSP. There's no units because one time Professor K said no units for KSP. It's just KSP. Okay. Moving on to B. Okay. Now, let's look at B. It's basically the same thing, except we're dealing with BiI3. And the S, whenever we forget the S, it's going to be 1.32 E negative 5 moles per liter. Okay, so same thing. Write it down, disassociate it. What was it again? BiI3, okay. And you have to look at there's a solubility chart or whatever chart that has the ionic charges that you have to see what's the charge for each. What's the charge for Bi and iodine? I don't even know what Bi is, I just know it's Bi, so I don't really need to know that. So yeah. Arrow there, this is the equilibrium arrow. Okay. Okay, so the ionic charge for this is 3 plus for the Bi. And it's obviously aqueous. Anytime it's disassociated, it's aqueous from a solid. This is a solid. So you already know this is going to be the S max, the BiI3, the reactant. Okay. So the iodine had a subscript of 3. So for that reason, we're going to make it a coefficient of 3. Iodine. And it has a negative charge. It's aqueous, of course. Okay. For this one, we actually make the ice chart. Okay. The rice chart. Rice chart, same thing. Okay. Got that. Cancel this out because we know it's the S max, it's solid. S max. So we actually don't know the initial. So 0, 0. This is 0. Actually, that's don't even worry about that. And so you bring this down. It has the bi. You bring this down. Bring it down. It has no coefficient. You can see. It's just bi. Don't worry about the ionic charge. Just no coefficient. Now plus s, and the reason being plus s is because like I said earlier, the q is going towards the right. It leaves behind negative and it turns positive. That's why the product side is positive. And it's going to K, SP, whatever. Okay, this is an S. Now, the iodine, you can see it has a coefficient of 3. So for that reason, we're going to do plus 3S. S plus 3S. That's all we know. That's what Bi and 3I is. 3 iodine. So the KSP, again, we don't write the S max, we don't write the solid, the reactant itself because it's a solid. Only write the aqueous in the problem. If it was a gas, you'd write the pressure, whatever. Bi 3 plus and iodine to the power of 3 because it has a coefficient of 3. Again, excuse my terrible handwriting. Okay. Equals S. And then it's 3S, right? Look, 3S. S, 3S. 3S, and we still write a power of 3. Okay. Okay. So this is it's just math. S to the S times. Okay, first do this. Do the power. 3 squared is 9. S squared is S squared. So S times 9S squared. Now when you multiply that, it's just not hold on. Sorry. Messed up. Forget that. Okay. It was S and then 3S cubed squared. I'm sorry. I wrote squared on accident. Okay. So obviously do the cube, do it on your calculator. 3 to the power of 3. What is that? 27. So 27 S cubed. That's what that is. Bring down the S, just bring it down. Okay, 27 S cubed times S. So you're just adding an S. Multiplying variables is adding variables. No way. Or sorry, exponent. I don't know. It's the variables. What's math? 27 S to the power of 4. Okay, now that you have S4, so go back up. you can see they give you the S, the mole per liter, 1.32 E negative 5. All right, let's get that down. 1.32 E negative 5. Okay, S equals 1.32 E negative 5. Okay. 27. Now plug S in for 1.32 E, or plug in 1.32 E negative 5 for S. 1.32 E negative 5, and then put it to the power of 4. So do this in your calculator. You do it in mine. 32 second E negative 5 to the power of 4. You end up getting 8.19708, but we'll just round the 8.197 to 8.212. Or no, sorry, 8.20. Yeah. Because 19 rounded to 20 equals to 8.20 E to the power of negative 19. Boom. There you have it. This be pretty. Okay. Okay, this is problem number 44. This is from chapter 17, I believe. Yeah. Okay. So the problem says the KSP for lead iodide is 1.4 E negative 8. Calculate solubility of lead iodide, each of the following. Okay. So there'll be three parts to the problem. All right, let's get it to it. So we're looking at the dissociation of lead iodide. Like all three parts involve the dissociation of lead iodide. Okay. And the only difference is the initials. Let me show you what I'm talking about. So first we got water. Okay. Create your. Well, first I guess write down lead iodide. Yeah, lead iodide. PbI2. PbI2. And this is a solid. When it disassociates, you have to look at your solubility chart or whatever has your ion charges. And this one is Pb2+. 2+. It's aqueous. Okay. Let me rewrite this. Oh god. Aqueous. Okay. As well as iodine. Now the thing about iodine, it has a subscript of 2. So what you're going to do is make that a coefficient on the other side, meaning like this. Okay? And look at let's see, what's the charge? Iodine, it's negative. It's at a negative charge. It's aqueous, of course. Okay. Now we create the ice chart. Let's get to it. See, we don't even need that. Just the ice chart. ICE. God damn it. Excuse me. Okay. Cancels it out. That's S max because solid. This is the reactant. You don't You don't do anything to it. Okay. Now so for water, it's just you take everything out. Like you disassociate it completely. Like take everything. They don't give you any initial, so it's just water. Like you take everything out. Can I just? You don't need that. Scroll it. Okay. So 0, 0. It's simple. This is just. It's like you're not even dealing with water. It's just simple, like simple disassociation. Well, you are dealing with water. Forget I said that. Okay. Uh, Again, like I said in uh the last problem, you have to look at the Q and the K, and for that reason, since the reaction is shifting to the right, the S over here will be positive. It'll be positive. Positive. Okay. Now you're right. Now just sum it up. 0 plus S. Actually, don't even write the 0. We don't need that. Just write S. S. Actually, oh shoot, I forgot. So this coefficient right here, before the iodine, it's a 2. So we bring down a 2 right here. Bring it down. So it's 2S because of this. Okay. Now that we have that. Now, if you look up here, we know the KSP is 1.4 E negative A. KSP equals to, and that's, I think it's for every reaction. 1.4, or I mean like every, every part to this problem, it's 1.4 E negative A. 1.4 E negative 8. Okay. Now, let's look at this. So, right, 1.4 E negative 8. 1.4 E negative 8. What exactly? I'll tell you. So, 1.4 E negative 8, it's lead and iodide. Not the reactant, because that's a solid, the two products, when it disassociates into themselves. That's not what I meant. I meant like just, yeah, just like disassociates, like separate. They become separate. Okay. So let's see. Okay, yeah, that's what you do. PB 2 plus. Yeah, you just bring whatever is on the product side, and then iodine. Subtract. Okay. Oh right, and don't forget, like I almost just did. Do not forget the exponent because of the coefficient. Okay. Now we can actually plug in all that we know for lead and iodine. So let's do that. 1.4. That's not a negative. 1.4 E negative 8 is equals to. Now what do we know for lead? We know that it's just S. That's all we know. What do we know for iodide? I'll tell you what we know. We know it's 2S. Okay. Oops. Alright. So S times 2s. What is it? That is 2s. Wait, sorry. Forgot the square. Okay. S times 2s squared. Now that 2s, well, first we do the exponent. 2 squared is 4, s squared is s squared. So 4s squared times s. So 4s cubed. That's 4s cubed. 4s cubed. Let's bring it down one more time. 1.4 e negative 8. Alright. Now it's just basic stuff. Basic algebra. Well, I don't know if this is algebra. Basic math. Divided by 4, divided by 4. 1.4 e negative 8. Second e negative 8 divided by 4. And now that is 3.5 e negative 9. 3.5 e negative 9. Okay, we're not done yet because it's s squared. So you find the square root, both sides. Box. Now that is 3.5 second e negative 9. Usually I would just do this in my head, but today I'm the teacher, so I have to show every step. 5.92 e negative 5. 0.92 e negative 5. Okay. Now that is your S. All that work, and you still have to do B and C. Okay. B. Same stuff, except the initial. That's it. Because water, doesn't really mess with the initial. That's nothing to do with PBI too. So, yeah. You'll see. Okay. 0.10 molarity PbNO3 squared. Okay, let me write that down. This is, wait, what is this? I'll just write that up, okay. Zero point 0 molar PB. What was it again? Or, no, 3 squared. Okay. Now that we have that, now we're disassociating lead iodide squared. No, not squared, sorry. Lead iodide, just lead iodide with the subscript 2. I don't really know the word for that. Brain's not really working. It's working enough, but yeah. Okay, now that we have that, PBI squared. Well, not, sorry. Why do I keep saying squared? Now we'll be disassociating that. Once you disassociate the equilibrium, look at PB plus 2I. Remember 2 because the 2 subscript turns into a coefficient. And then you look at the solubility chart for the charges. I'm just going to look at the first example because I can. 2 plus and negative. So 2 plus negative. Okay. ICE. Gotta love the IC. Okay. This is alright. This is a solid. Shit. Whoops. Okay. This is a solid. Aqueous. Okay. This goes out because it's a solid. Blah blah blah. S max. I don't know. Just simple X will do. Okay, now this is what makes this different from the part A. It's 0.10 PbNO3 squared. So plug that in right here. Pb. It's Pb, right? Pb. So 0.10. Okay. Don't really say anything about iodide, so 0. That's a 0. Okay. Okay, so this has a 2 coefficient, right? So that's why this will be 2s, just like in the previous, in part A. This has no coefficient, so it's just s. So this goes down to 0.10s, and this goes down to 2s. Okay, now we're ready for the KSP. The KSP for this problem is equals to, what is it equal? 1.4 negative 8, just like the other problem. Okay. We're gonna find the S. That's the mode, find the S. That's the goal. Okay. 1.4 negative 8, that's the E. So what you do now is, what are the concentrations? We'll bring the 1.4 E negative 8 right here. Okay, and that equals to what? That equals to the concentration of the 2 aqueous solutions, which are Pb and iodine. Okay, so Pb, I think Pb's lead, I'm not sure, but I can't get points off for not knowing lead, right? If it's lead or not, I don't know. Ionic charge for iodine is minus. It's squared because the coefficient, whatever. So what do we know for Pb? What we know is it's 0.10s right here. 0.10s. That's pretty much all we know. 0.10s. Okay. And what do we know for iodine? It's 2s. 2s. And you still write the square. Okay. Now you multiply these together. First off, let's get this exponent out. Shit, I forgot about this. 1.4 e negative. So 4s squared. 4s squared. That's what it is. 4s squared. 0.10s. Okay. Again, this is just math. Math. How would you do this? Okay. I think the math was tricky, but I'll get it. Let's see. Okay. I think I messed up right here. Yeah, I messed up. I don't think I was supposed to get to this part. Sorry. Okay. Let me erase this part. Okay. Let's see. 1.4 e negative 8 is equals to this is where I messed up. Okay, so I'm sorry, I messed up right here. I was supposed to write plus s. That makes sense. Okay, sorry about that. 0.10 plus s. Okay, I was like so confused. 0.10 plus s. Oops, that's a 5. Okay, plus s. And that is, the iodine is 2s squared, right? 2s squared. Okay. Let's see. What now? Now we make an assumption. Let me actually write this. Okay, no. So negative 8. Negative 8 greater than, to make the assumptions greater than 3, blah blah blah. Assumption. There's rules to it. So we're left with 1.4 e negative 8 is equals to 0.4 s to the power of 4. Okay, 0.4, 0.4, 0.4, take that out. Blah, blah, blah. Do it on your calculator. Negative 8. 3.5 e negative 8. 3.5 e negative 8 is equals to s to the power of 4. Alright. I don't know what this is called. I know square root, I know cubic root, but I don't know. I'll just call it root 4. If that makes sense. I don't know. So you would just take 4 square root of... Wow, that's so bad. Okay. Oops. Okay. God, what am I doing? Sorry. Okay. There. Go for 3.5 e negative 8. Okay. Is equals to s. S and s. And if you do that on the calculator, you will realize you will get 1.36. Let me just do it real quick. Give me 1 second. forgot what the root Q. Okay, I found it. Well, you get 0.01367784. So what we can do is we can write 1.37. Sorry, no. Hold on. Take out the 6. I'll just write 1.37 e to the negative 2. Negative 2. Now that's the S for the... I thought that was just... I thought B was going to be just as easy, but whatever. Okay, that's your B. Okay, now it's time to do C. Alright, C. Let me make sure. Okay. C is 0.10 molar sodium iodide. This would be the initial. Okay. This would be, since it said iodide, I think guessing it would be the initial for the iodine instead of the lead this time. Let's see. Molar NaI. Okay, same thing, just disassociate the whatever. Yeah. Can't believe this is taking so long. Took longer than I expected. Okay. EQ plus 2i. It's just, I'm just copying what I wrote from B. Same thing. For the equation, it's the same thing. Aqueous solid, okay. Now you create the ice chart, okay. Boom, S max. Take that out. Okay. Now this is where the change happens. Did I write that right? Yeah, I did. Okay. Well, let me check real quick. Yeah, I wrote that right. Okay. So it says sodium iodide, right? It doesn't mention lead. So that stays 0. And again, Q, K, whatever, like I said in the last problem, yeah, plus S. That's the reason why it's plus is because of the Q. Like I said. Okay. Now they give us the iodide, no sodium iodide. So you can write 0.010 molar. Okay. 2i 2s. Sorry. Oh no, I over 2i. Okay. 2s because of the coefficient. Bringing that down. 2s. Okay. S 0.0 messed up my 0. 0.010 plus 2s. Okay. Now, whenever we write the concentration, we're going to substitute this into the concentration. But first, let me write this down. So the KSP like it was for the last two problems, it is okay, it's 1.4 e negative 8. 1.4 e negative 8. Okay, so bring that down. 1.4 e negative 8 is equals to the concentration of the, what do you call it, Pb2 plus and 2I minus, or I minus squared. P2 plus I minus squared. And how do you explain why we don't write PBI squared, the reactant? Because it's a solid. Okay, now what do we know for lead? We know it's an S. That's all we know. What do we know for iodide? We know it's 0.010 plus 2S. Okay. 1.4 e negative 8. Oof. It's a lot of work. And the square too. Okay. What do you do next? I always mess up at this point. Right. Assumption. 2, look at 2 and 8. Has a difference. 2 and 2 and 8. Difference of 6, and so that's why it will be. Well, it has. I just know has a difference greater than 3. That's all I need to know. And for that reason, we can make an assumption. And the assumption, to get the assumption, 1.4 e negative 8 is equals to S. All this goes out. (0 e negative 2). Same thing like we did in the last problem. Okay, 1.4 e negative 8 is equals to 1 e negative 4. One sec. Sorry. Hold on. Okay. Ooh. Okay. So it's pretty simple. Just take that out. Bring it to the other side. Basic algebra. If you do it in the calculator, you end up getting you end up getting 1.4 e negative 4. That is your S. Okay, this is the first, what do you call it? This is the one and only problem for chapter 17. Consider the reaction. And this is problem number, sorry, couldn't get the number, but this is actually problem number 68? Yeah, 68. Okay. So let's see what they want. Consider the reaction. 2 phosphorus, oxygen, chlorine turns into 2 PCl3 gas, SO2. So we're dealing with gas. Okay. Calculate G for this reaction. GF values for POCl3, PCl are... Okay, let's work on A. Calculate G. Okay, the G equation. So to calculate G, G naught, not just G. You need to do products minus reactants. Let me tell you what I'm talking about. That's the worst triangle ever drawn. The history of triangles. Delta G, R, X, N. And moles, that's the N, moles. G, F products, this is products. Oops, sorry. Products minus to N delta F of the reactants. Now this is the equation. Let's start plugging this stuff in. Okay. Oh my god. Okay. The products. We have 2 products. Excuse me. Forgot the equal sign. Okay, so we have 2 products. PCl3 and O2. So let's do the PCl3. Okay. 2 times GF. Excuse me. G naught FF PCl3 CL3. And then well, the reason why it's 2 actually is because of this coefficient right here with before PCl3. And O2 doesn't have a coefficient, so we're just going to write simply 1 mole of G, sorry, that's a G, F, O2. This is a 1, this is a 2. 1 and a 2, okay. So, yeah, okay. So let me get started on the reactants. There's only one reactant, which is 2 POCl3. So we only have 1 mole of 2. And then 2 delta naught of G F POCl3. I didn't write 2 POCl3 because I wrote the 2 before, so just making sure. Okay, now we start plugging it in. 2 times, all that just turns into, let's see what they have written over here. So for PCl3, they have negative 502. So negative 502. Actually, hold on. Something's not. Oh my god. Blunder mistake. I just wrote whatever's closest to it. POCO3 and PCO3. So PCO3 is negative. It's actually negative 270. 270. Okay, and the other thing was 1 times O2. 1 times, what was O2? What? They don't have O2? So confused. Oh, okay. They don't have O2, so you don't write anything. Just cancel it out. There's nothing there. And the units for this is kilojoules. You should just write joules for now. Joules per mole. Okay. Let's see. Wait, sorry, this is kilojoules. My bad. I thought I thought they would give us whoever made this textbook, I thought they would trick us with the kilojoules. I guess not. Okay. POCO3. POCO3 is what? It is negative 502. Negative 502. Write that down. Negative 502. Cool. Okay, we're getting somewhere. Let me just do this on the calculator real quick. Negative 270 times 2 is negative 540. Negative 540 kilojoules. Now that's the product side. And negative 502 times 2 is negative 1004. Oh shoot, hold on. Part of the equation is actually a subtraction sign. I just noticed that right there. So this negative 540 minus 2 times negative 502, which is, so this turns into a plus because it's negative 1004 kilojoules. This turns into a plus because this was originally negative 1004, and negative minus negative turns into, or negative and negative is positive. So because of this, negative, positive. This is my little triangle. Yeah. Okay. All right. You do this on the calculator, you get delta G. Let's finish this up. Delta G naught to be 464 kilojoules. Okay. Is the reaction spontaneous under standard conditions at 298K? Well, delta G is positive. So this makes it non-spontaneous, because for it to be spontaneous, delta G has to be negative. easy. Okay, now C. The value of S for this reaction is 179 kilojoules. Joules, what? Joules per Kelvin? Yeah, joules per Kelvin times mole. What temperature is the reaction spontaneous at standard conditions? Oh boy. Oh man. Last question. Let me finish this right. Okay. So what we do on this one is what do we do? Okay, what do they give us? They give us the S, change in S, delta S, and they want us to assume that delta H and delta S do not depend on temperature. And they want to find the temperature at standard conditions. Okay. Let me write down what I know. So delta S naught is equals to 179. Is it kilojoules or joules? Oh man, just had to put joules in there. Joules. Kelvin times whatever units. So to find the delta G equation is delta G. Sorry, my triangle failed. Delta G naught is equals to delta H naught minus temperature delta S. Okay. That's pretty straightforward. That's the delta change in G naught or delta G naught equation. This is a formula, sorry. So what do we know? Okay, so we know delta G naught from the previous part A. We know it to be, let me convert that to joules real quick. Okay, this is actually 464,000 joules. And shoot. Okay. Yeah, so apparently I forgot to tell you this. I forgot to mention this. I have to manipulate the equation. It's not equals to, it's the manipulated equation. Let me look for it real quick. My cheat sheet. Okay. It's delta G of naught plus T delta. I thought it was inverse log, but whatever. Okay. Minus delta H naught. Okay, 464,000. We're using this equation to solve this. We manipulated this one. Manipulated this equation to get that, and then we're using this equation to do this. Okay. So the equation change in delta G naught plus temperature delta S naught. So the temperature, it's under standard conditions, so it's 298. Okay, 298K. And delta H naught. That's interesting. Okay, hold on, let me solve delta H. Sorry, delta S. What was delta S? How do you get delta S? Oh, right. Okay. So I have to look at the little chart thingy. Let's see. Okay. And then 179 volts. Okay. Oh, sorry. Hold on. Volts times mole as well. Moles. Can't forget the moles. Okay. This is actually equals to. Now that all equals to delta H naught. And delta H naught is actually, we have to solve for that real quick. Let me do that. That's really simple. So the temperature equation is delta H naught over S. Let me write that down. Delta H naught over S naught. Delta H S naught. So we know temperature is 298. Okay, 298. Delta S is what? 179. 179. Okay, you multiply that, you get delta H naught. Okay. Actually, no. I'm sorry. We need to find, this is actually not used to solve delta H. Delta H is, no, 179 was actually given to us. So, delta H. Oh, okay, good. Delta H is actually whatever all this is, which is this at the end of the day equals to 517. At the end of the equation, it equals to 517.342 joules per mole. Okay, we know all that. All right, moles cancel. Volt does not cancel. Kelvin cancels though. Okay. Now, this is the last thing we need to do. Temperature equals delta H naught over delta S naught. This is what we're looking for, the whatever they're asking for, temperature. So we know delta H to be 517.342 joules per mole. Okay. And delta S, well, what did they give us? They gave us delta S to be 179 joules per Kelvin. This actually has a Kelvin in it. This is where the Kelvin crosses out with. Sorry, I forgot to add that. Yeah, 179 joules times Kelvin times mole. Okay. Do this on the calculator. Moles cancel, joules cancel. You're left with Kelvin, by the way. That's it. So after doing this, the calculator, 517.342 divided by 179. This gives you 2890.17. 2890. That's all I'm gonna do. 2890. That's good enough. And this is the answer to the question. Sorry it took so long, but thanks.